Okay, Bismillahirrahmanirrahim. Assalamualaikum. Hi everyone. Okay, today I just want to share with you guys the summary on the topic regarding the flexure of the beam. Okay, so the analysis of the beam section under flexure, which is you already studied in the chapter 4, but today I'll make this video just for the summary, which is I will summary on the stress block, the identifying the singly or doubly reinforced, and also how to calculate the required reinforce for both cases. Okay, and first of all, we need to know what is the beam, or how the beam is under the flexure. Okay, so in this figure, it shows that this beam will have a load and on top of the beam, and on the bottom will have the tensile stress. Okay, so this figure shows that the beam is under flexure, which is underside of the beam is in tension. Okay, so we can see here in the middle is the neutral axis. On the bottom we will have a tension zone, whereby, and on the top we will have a compression zone. So this will have a failure, or we call it failure flexure. Will have some crack on at the bottom of the beam. Okay, so this is a cross section of the beam, which is we have the overall depth, effective depth, area of the reinforced, and also the breadth. So flexure is the action of the bending or curving or condition of being bent or curved. Okay, so usually this deflection shape is under pressure due to the load on top of it. Okay, so this UDL, which is the uniform distributed load with this simply supported beam, will induce the flexure. Flexure is the condition whereby it will become bent or curved. Okay. Okay. So we proceed with the rectangular beam cross section. So as shown here, we have a simply supported beam. So we have a beam section, beam cross section. So here I will show you the difference between the singly reinforced beam and also the doubly reinforced beam. Okay, for the case, for the width or breadth, both cases are same. Okay, so both will have the height, overall height, and will have the effective depth, which is from the top of the beam until the middle of the area of middle of the steel bar, main steel bar. Okay, so in singly and doubly reinforced, both will have a tension steel. Okay, on top of concrete of the beam will have a compression, right? So at the bottom we'll have the tension region. So for the singly reinforced beam, the steel reinforced is only present in the tension region. Okay, whereby for the doubly reinforced beam, the steel area present in both area, which is they will have a steel in the tension area and also steel in compression area. Okay, for the doubly reinforced beam, we will have the AS prime, or we can call as a AS2, which is the area of the reinforcement for the compression steel. And for the case for the doubly reinforced, we will have the D prime, which is D prime is the effective depth of the compression reinforced, which is sama juga from the top until the middle of the steel bar. Okay, so this is the ultimate design moment, which is calculated from the design load. So we got the SFD, we got the moment. Okay, then ultimate resistive moment is depends on the material strength and also the size of the dimension. Okay, for our design objective, the ultimate resistive moment MU must be greater than ultimate design moment, which is MD. Okay, for this case, we can proceed with the singly reinforced. On the other hand, if we got the sebaliknya, so that's mean we need to propose the beam become the W reinforced or change some of the material or the concrete grade. Okay, so the ultimate resistive moment ni dapatnya MU is will be determined by using the stress-strain relation for the design of the cross section, whereby for the ultimate design moment we can calculate under the ultimate design load, and for example, for simply supported beam with uniform distributed load, MD is equal this equation. Alright, so this is our design objective. Okay, this is one of the important part. This is the strain, which is the stress-strain relation, ataupun kita boleh panggil dia as a stress block. So we already know that beam consists of two regions, which is the compression region and also the tension region. Okay, so in this figure shows that on top of it we'll have the compression and at the below we'll have the tension. Okay, concrete section will have a natural axis. Okay, so the strain will become like this. So this is the ultimate strain for concrete and this one for steel, and this is the stress at the limit state. Okay, so this is the alpha ataupun the coefficient for stress, FCK divided by the its partial safety factor. So we got this value of stress. Okay, same as for the steel. So the characteristic strength divided by partial safety factor will have this value for the stress. Okay, and X here is the distance of the from the top of the beam to the natural axis. Alright, so this is the strain and this is the stress. Okay, in class in Eurocode, it allows us to use the simplified stress-strain relationship. Okay, maksudnya yang kita nak guna adalah this one, the simplified one. The simplified one is because of this parabolic. Kita tak nak macam ni, so kita simplifiedkan dia menjadi square. So the simplified stress will have this stress value, but the height of the stress block is 0.8 x, ataupun ni somehow kita kata S sama dengan 0.8 x. Okay, so in order to calculate the force, is we know that x is the distance from the top to the natural axis. So S is the simplified one, which is S sama dengan 0.8 x. Z is the moment arm, which is the lever arm. Okay, then FCC is the forced concrete compression, FST is the forced steel tension, FSC is the forced steel compression. So for FSC is at the compression side, FST is at the tension side. Okay, so we noted that forces is the stress times with the area. So we got this value for the forces. So force is the stress times with the area. So, okay. So the figure D is the simplified one. Okay. So we are using 0.8 as the depth for easy calculation, and D and this one is for calculating the forces. Okay. Okay, this is the stress block for the singly reinforced beam. Okay, we only have the FCC and FST. So Z here, we can also calculate by using D minus half of the S. So D minus 0.4 X. Okay, so we know that moment is the force times with the distance. So here is moment times with for the equilibrium. Okay, for the case for singly reinforced, so for the equilibrium state, the ultimate design moment is equal to moment of resistance of the section. So FCC times Z is equal to FST times Z. Okay. And for doubly reinforced, so in the compression part, we will have two forces, which is force coming from the steel in compression, and the second is the compression from the concrete. Okay. For calculating the moment at the equilibrium, we will have the compression part equal to tension side, which is the FSC times Z plus FCC times Z is equal to FST times Z. So that means for the doubly reinforced, we will have two terms in the compression part, which is FSC, FCC. And FST is only at the tensile region, tension region. Okay, I think we can calculate by using this equation in order to find the area of the reinforced required to calculate the reinforced required for the beam that we need to know. Alright, so this is the W reinforced. We will have FSC, FCC, FST. How on the other hand, for the singly reinforced beam, we will have only FCC and FST, which is this one is coming from the compression. This one is coming from the steel in tension. This is coming from the concrete. I think that's all for this chapter. Okay, I hope you guys had more clear regarding this topic. Alright, thank you. Assalamualaikum.